This is chapter 7.1, Homework Solutions from the textbook. The first set of problems we had were problems 7 through 10. Instructions are to determine whether the graph can represent a normal curve. Key term here is normal curve. You need to remind yourself what is a normal curve. There's a picture of a normal curve. We had a normal curve is what we would call the bell-shaped symmetric. So this comes from our notes. And then we use that to calculate the areas, which were probabilities. And so in order to do those problems, we need to recognize some of the properties of a normal distribution, and there was a list of them in terms of that. So that's all we're doing on this problem. So looking at the first one is not, this is not normal. And what I see here to determine that it's skewed, so that's why it's not normal there. We get skewed distribution there. I would say this one here is normal. This one is a normal distribution. Has symmetry, starts low, goes high, comes back down. Has an inflection point where it kind of changes direction. That is a normal distribution. This one you might be fooled and think it is normal, but it goes below the x-axis. Remember, this represents the area. We use that to represent how many people, like in a relative frequency, so they can't be negative values here. So these are negative here. So this is not normal. And again, that's because we end up with this, it goes below the axes, which then says there's a negative relative frequency, which we don't have in a normal curve. This one again starts to look like it, but the fact that it goes back up here is the issue here. So this is also not normal. Before we move on, it's probably important to recall the other distribution we studied in addition to normal was the uniform distribution. So the graph was the same value across. This was uniform. So that is in comparison to the normal ones that we have here. So that's problem 7 through 10. Let's move on. Now take a look at problem 18, which is a uniform distribution problem. And so in order to solve this problem, we do need to represent its graph. And what we care about, we're looking at the x, some random variable x from 5 to 10. And so this represents the reaction time in minutes of a certain chemical process follows a uniform probability distribution, meaning that the probability that the chemicals will react within 5 to 10 minutes is uniform, meaning it's the same chance, equally likely. And this was similar to the example we did in class with, I think, the United Postal Service or Parcel Service question. And so there is our uniform distribution here. There's our density curve here. Now, this axis is the probability, which we don't know. We know it's uniform. It has to be the same value. I don't know what this value is yet, but we'll determine that right now. So how high is this? How high is this value here in terms of the probability? What we need to remember is for these probability distribution situations, the total area is always equal to 1 because we're talking about probability, and 1 is equal to 100%. So if we know this distance here is 5, right, from here to here the distance is 5, the total area here has to be, let's highlight that, the total area here has to be equal to 1. This total area that I've highlighted has to equal to 1. And so in order, 5 times what equals 1? So in order to find what 5 times what equals 1, so that value here has to be 1/5. And so we now know how high this is. And so what is the probability that the reaction time is between 6 and 8 minutes? Well, here is 6, here is 8. And so what we're trying to do in this case is calculate the area of that rectangle. And so that rectangle for part B becomes a distance of 2 because it goes from 6 to 8, 1/5 here. And so the probability that the reaction time is between 6 and 8 is going to be 2 times 1/5 or 2/5 or 40%. And so that's our answer for B. Moving on to C. What's the probability that the reaction time is between 5 and 8 minutes? 5, 8 minutes. That distance is 3. 3 times 1/5 is what you're going to get, or 3/5, which equals 60%. And then the last question, what is the probability the reaction time is less than 6 minutes? And so here the probability, that's for D, the probability that it's less than 6 minutes is that's going to give us a distance of 1 here. So this is just 1 times 1/5 or 1/5 or 0.20. And so then we have those values there. Okay, let's move on to problem number 28. The graph of a normal curve is given. Use the graph to identify the values of mu and sigma. Mu again, mu represents, this is mu, how we say that? So you got to use those words. This is the population mean, and this sigma equals the population standard deviation. Again, you're going to see those, you're going to see that notation, so get used to that, please. And so use this to identify that. And so this is exactly what we had done before in the past, where we draw our line and then mark off by standard deviations. So in this case, what we know is that the mu is equal to 530. And if we mark off by standard deviations, the standard deviation is 100. That's it. And so this, again, just to remind us of how we're going to label our normal distributions and then be able to do some calculations from that. That's problem number 28. Moving on to problem 34, the last one on this assignment. The heights of 10-year-old males are normally distributed. So again, we don't have the data, but because we know it's normally distributed, what we know is that we know the mean and standard deviation. We know the mean is equal to 55.9. And then what we know is we're able to mark these off by standard deviations. And so in this case here, we're able to then draw what this distribution looks like. We can get an approximation without knowing what all the data is. We can get an approximation of what the histogram would look like with this normal distribution looking like that. Draw a normal curve with the parameters labeled. So I have the mean, and then now everything is up by 5.7. So after one standard deviation, this would be equal to 61.6. Add 5 more, that's going to be 67.1. Add 5.7 more, and that's going to be 72.8. And so that's our distribution there. Label coming back the other way, subtract 5.7, so this is 50.2 right there. Subtract another 5.7, and so 52.7 minus 5.7, so that would take us down to 44.5. And then take it down another one. This would be 39, 38.5, 38.8. And so there's our draw with the label. Shade the region represents the proportion of 10-year-old males who are less than 46.5 inches tall. So now I know 46.5 is somewhere right there. Let's change the color. Right there is 46.5. Shade the region that represents the proportion that are less than. So that's going to be all of these people here are less than 46.5 inches tall. Suppose this area, let's say that area in green is equal to 0.0496. What does that mean? That means, and now this goes back to our notes, way back somewhere in our notes in chapter 7. To answer this question, I said it's important to know. Let's see if I can find it. I said important to know, important, right there. There it is. In our notes, I said important. Suppose the area under the curve represents the proportion of the population with that characteristic, or the probability that a randomly selected individual from that population will have that characteristic. So we can interpret that two different ways. And so what does this mean? It means that 4.9, so one way, 4.96% of 10-year-old males are going to be less than 46.5 inches tall. That's one interpretation. The second interpretation for this would be that the probability that a randomly selected 10-year-old the probability that a randomly selected 10-year-old is 46.5 inches or smaller is 0.0496. There it is. Those are interpretations. That's the homework for 7.1.